All right, now we're going to look at Pascal's principle, which mathematically is a very simple idea. Pressure at one place equals pressure at another place connected by a fluid. Let's think about this in words, first in a technical sense, then a little easier sense. An external pressure applied to an enclosed fluid is transmitted unchanged to every point in the fluid. That means if you have a container and you fill it with a fluid, like say water, and then you push on the water with some pressure P, and we'll say that P includes the atmospheric pressure, so that's an absolute pressure, and then you check the pressure at any place in the water, you will always find that the pressure is the original P you put in. So when you push on one place on a fluid, that pressure is transmitted to every part of the fluid. I like to relate this back to the ideas from Newton's second law that connected objects must have the same acceleration, and say that 2 points connected by a fluid have the same pressure. So any points in space connected by a fluid in a container get the same pressure, just like connected objects had the same acceleration. Now, we're going to talk more about uses for this on the next slide, but we can take the fact that pressure is force over area and rewrite both sides of this equation as the force at one place divided by the area at one place equals the force at the second place divided by the area at the second place. So it's just writing each of these P's as an F over A. This here is the more useful form of Pascal's principle, and you'll see on the next slide why. Okay, so let's talk quickly about a couple ways we can use Pascal's principle. Let's consider a hydraulic lift, which is a car jack. And I'm going to give you one more way of thinking about Pascal's principle as we consider it. If the pressure increases at one place in a fluid, it increases by the same amount throughout the entire fluid. Remember, I said that pressure at one point is equal to the pressure at another, meaning the force over the area at one point equals the force over the area at another point. We exploit, or use to our advantage, this idea here in designing jacks to lift up cars. So if you've ever lifted a car up with a jack, if you tried to lift up the car with your hands, you'd have to put a really big force on it. But if you use a jack, you're actually not pushing anywhere near as hard as you would have to if you were lifting up the car with just your hands. The way a jack works, you have put in a very or comparatively tiny force on one side of the jack. And so let's think about this. We've got F1, this is what we're putting in. And on the jack, the area you put that force is intentionally made very, very tiny. So our area 1 is very tiny, and our force 1 is pretty small. So we've put in a small force over a tiny area. Now, because that area is tiny, this actually means that we get out a big pressure. So over here, all the stuff we've put in, I've written in green. Small force on a small area, creating a big pressure, mainly because that area is very small. So think about small number in the denominator means the fraction's pretty big. On the other side of that equation, we have what we get out. Now, the pressure has to stay the same, so it has to be that same big pressure in and out. On a jack, the area on the side coming out, the side that pushes up the car, is very big. So our area 2 is very big. Now, if you have a big denominator in a fraction, that usually means the fraction is small. So the only way to keep these two sides of the equation equal is if our force coming out is also very big. And this is how we're able to lift up a car with a jack, is we put a small force in over a small area, and then on the other side of our jack we make the area very big, and according to Pascal's principle, that means that the force has to be very big coming out, because the pressure in this entire tube has to stay constant. So the pressure in that tube has to be constant. And if we try to spread out our pressure over a large area on one side of the jack, we end up with a big force. because the P everywhere has to be the same. And that's how we build jacks. A similar idea is used in designing the brakes in your car. You put a pressure in, and then your brakes are connected to the brake pedal by a fluid, and so that fluid transmits the pressure. That's more just about using fluid to connect two devices than it is about exploiting it to get a big force out of it. The brakes in your car just transmit the force from your foot to the brakes. All right, that's it. This last side, super important. Might want to watch the last 3 minutes again and think very carefully about, since the pressure has to be the same, how we can use that by changing up the areas. That's it. See you tomorrow.